Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you enjoy the podcast, show your support with a like, a follow, or comment. It's free for you, but means the world to us. Let's keep leveling up together.
It is great to be back.
So today we are looking at a massive shift in how things are made. And look, I know we hear game changers every other week in this industry.
All the time.
But today I don't mean a small change or, a new button in SolidWorks. I mean a fundamental rewrite of the rule book.
Yeah, total paradigm shift.
Exactly. We aren't just talking about CAD drawings anymore. We're talking about systems that evolve geometry the way nature evolves bones.
Right.
Cars that can physically fix themselves while sitting in your driveway, and the AI co-pilots making it all happen.
That's right. And our mission for this deep dive is really to walk through that story, the story of the modern digital engineer.
Okay.
We're going to trace this chronologically so it all makes sense. We'll start with the birth of the digital twin at NASA.
Back in the space race.
Back in the space race. Then we'll move into generative design, where the AI actually takes the wheel. And finally, and we have to do this, we look at the risks.
The scary stuff.
The scary stuff. What happens when these incredibly powerful tools get into the wrong hands?
I was reading through the source material you sent, and I have to say, there were some serious aha moments.
Oh, yeah.
Specifically, a NASA bracket that looks like it belongs in an alien autopsy and a ransomware concept that learns how to play you like a video game. But okay, before we get there, let's start with the foundation, the digital twin.
The digital twin. It's a buzzword we hear constantly.
Right. And usually when I hear digital twin, I just think of a really high fidelity 3D model, of fancy assembly and KTS spinning on a screen. But you're telling me that's too shallow.
Way too shallow. If you just have a 3D model, you have a digital shadow, not a twin.
A shadow. Okay.
A true digital twin, or DT, is a synchronized link with a physical object.
Oh.
Imagine a turbine in a factory or a car on the road. The DT uses data from embedded sensors to simulate the real-time status of that object.
So it's not just the geometry, it's the state.
Exactly. If the physical object heats up, the twin heats up in the simulation. If the physical object starts vibrating at, say, 40 hertz, the twin vibrates at 40 hertz. It's a living mirror.
That distinction is crucial. That is the difference between a photograph and a live video feed.
Perfect analogy.
But where did this start? Because I'm guessing we didn't have IoT sensors back in the day.
We did not, but we did have the Apollo project. And this is the origin story.
Okay.
NASA had this massive logistical problem. I mean, once you launch a vehicle into space, you can't exactly pop the hood to check on a rattling noise.
No physical access.
Zero. So they essentially built two of them, two space vehicles. One went on the mission and one stayed right here on Earth. The twin.
That sounds incredibly expensive, but I guess it was necessary. So if an oxygen tank explodes on Apollo 13...
You test the fix on the Earth twin first. You see if it works before you tell the astronauts a million miles away to try it. It mirrored operations to allow for troubleshooting. That was the grandfather of the digital twin.
High stakes, high cost, and all manually synchronized.
Exactly.
Okay, that's NASA. They have the budget for 2 spaceships. But how does this, fast forward to today, how does this concept look in my driveway? Because I don't have a second car in a lab mirroring my commute.
No, but a server does. And the best example right now is Tesla, specifically the Model S.
Right.
Tesla uses digital twins to design their cars. But the magic happens because they keep them connected. The cars are constantly talking to a remote center.
And this is more than just GPS or Spotify updates.
Much, much further. So here's a specific story that really highlights the power of this. Back in 2013, there were reports of 3 Model S cars experiencing burnouts.
Burnouts, so fires.
Essentially overheating issues that led to fires, yes.
Yes.
Now, in the old world of automotive engineering, what happens next? That is a massive physical recall. You're sending letters, people are driving to dealerships, waiting for hours. It's a logistics nightmare.
And a PR disaster. But Tesla used the digital twin approach. They analyzed the data streaming from the cars, the digital twins of the entire fleet.
So what did they find?
They realized the problem wasn't a defective part necessarily. It was an issue they could fix by changing the suspension clearance at highway speeds and altering the charging settings.
So the car was riding too low and hitting debris on the road?
Partly, yeah. So they pushed an update. Over the air, they effectively fixed a hardware vulnerability with software. The problem was solved without the owners ever having to open the hood.
That is wild. I mean, it just changes the entire economics of maintenance.
It does, and it lets you do what we call predictive maintenance. You can re-engineer the life of a product, like doing fatigue analysis on an aircraft wing without destroying the physical object.
You're simulating the stress on the digital version to save the physical one.
Precisely. It's a game changer.
It's like having a voodoo doll, but you use it to heal the person instead of hurt them.
That is actually a surprisingly good analogy. I might have to steal that one. Feel free. Okay. So that's monitoring things. That's keeping an eye on what already exists. But the sources you sent over suggest an even bigger shift is happening in how we create things. This brings us to generative design.
This is where the role of the engineer really starts to change. Traditionally, engineering is, well, a human sits down, stares at a blank screen, and draws a shape.
I think this bracket should be a square with a hole in it.
Exactly. Then they run a simulation to see if it breaks.
Right. Iteration 1, it breaks. You make it thicker. Iteration 2.
It's manual trial and error. In generative design, the human doesn't draw the shape at all.
So what do? Just ask the computer nicely.
Yeah.
Please make a bracket.
Almost. They define the requirements. They tell the computer, I need a part that can hold this much load, uses this material, and very importantly, stays out of these specific zones.
Okay.
And then the AI generates the shape. It sounds a bit like those AI art generators everyone's playing with now.
It is the exact same concept. One of our sources uses the analogy of DALL-E. You type in an armchair in the shape of an avocado, and it creates it. It explores the latent space of possible images to find one that matches your text.
An avocado armchair. I would sit in that.
Sounds comfortable. But in engineering, we're not making avocado chairs. We're making titanium-spaced parts. The stakes are a lot higher because physics doesn't negotiate.
Good point. So give us a walkthrough of a success story. I'm a little skeptical. Is the AI actually finding better solutions or just weird ones?
Let's look at the NASA Goddard Space Flight Center. They have this process called evolved structures.
Okay.
They were building something called the Excite Tip-Tilt Bracket for a balloon mission.
The Excite bracket. Sounds intense. What were the constraints?
It had to hold a sensor, sure, but the main challenge was shock. It had to survive a parachute landing. We're talking about a 10G vertical load.
10 Gs. So if that bracket weighs a pound, it suddenly feels like 10 pounds. Instantly.
Right, and it couldn't block the light paths for the instrument. So NASA set up a showdown. Man versus machine.
I love a good rivalry. So, the human team.
An expert designer and a structural analyst. People at the top of their game.
And the AI team.
One engineer. And his only job was to encode the requirements into the software.
Okay, so what happened?
The human team worked for 2 days. They went through 4 different iterations. They struggled to balance the stiffness and the weight.
And the AI team?
It took about 30 minutes of human time to set up, and then the AI just ran for an hour.
So it's faster? I mean, that's not surprising. But was the design actually better?
Significantly better.
Right.
The human designs were either too heavy or, in their final attempt, just unmanufacturable. It looked good in CAD, but you couldn't actually build it.
Ah.
The AI design, however, well, it looked weird. It looked organic. It looked bone-like.
When you say bone-like, what do you mean?
It looked like the inside of a femur, all these messy, intricate structures. And that happens because the algorithms use topology optimization. They just remove material that isn't carrying stress, which is exactly how nature evolves bones. It's a principle called Wolff's Law. If a part of your bone isn't bearing a load, your body dissolves it to save energy.
And if it's under high stress, it adds more material there.
Exactly. So the AI is basically simulating millions of years of evolution in an hour. It doesn't care about looking pretty or geometric. It only cares about the load path.
And what were the final stats on that?
The AI part was 3 times stiffer and significantly lighter than the best human attempt. Plus, it was designed for digital manufacturing, so they could send the file straight to a 3D printer.
That's incredible. You're talking about development time dropping from months down to days. And you get a better part.
It's not just about speed. It's about breaking out of human bias.
Yeah.
We like straight lines and 90-degree angles. Nature doesn't.
But this raises a tough question. If the AI is so good, faster, stronger, lighter, why do we need the humans at all? Why not just hit print on a car?
Because of something called the complexity trap.
Okay, let's unpack that. What's the complexity trap?
Think about a modern car. It's not just an engine and wheels anymore. It has 80s, advanced driver assistance systems. It has heated seats, infotainment, hundreds of sensors. All of that needs power and data.
Which means wires.
Miles of wires. The Siemens source highlights this perfectly. The wiring harnesses in modern vehicles are massive. They're incredibly intricate. You simply cannot draw every single wire manually anymore.
So you reach a point where the human brain is the bottleneck.
It is the bottlenecks. You need something called wiring synthesis. You set automated rules that generate thousands of connections and splices. But here's the catch, and this brings us to this idea of next-gen AI.
And how is next-gen AI different from, say, the chatbot I use to write emails?
Well, current AI, like those chatbots, is based on large language models.
Yeah.
They're great at text and images, but
Yeah.
they struggle with physics. They hallucinate.
What does a hallucination look like in an engineering context?
It looks like the AI is suggesting a material that doesn't exist, or designing a bolt that goes straight through a fuel tank.
Right. Not good.
You don't want an AI hallucinating the brakes on your car.
Definitely not. So we need constraints.
We need first principles. Next-gen AI is designed to adhere to physics and manufacturing constraints. It has to be grounded in reality.
So where does the engineer fit in this new world? If the AI is generating the geometry and checking the physics.
The role shifts. The engineer becomes a co-pilot. They stop doing the rote tasks like verifying every single bolt or drawing every wire. Instead, they define the problems. They become the architect of constraints.
Architect of constraints. I like that title. Sounds important.
It is. It's a human-centric approach. The AI points the engineer in the right direction, but the human has to be there to stop the AI from designing something unsafe. You need that oversight.
So the AI answers the question, but the human has to ask the right question.
That's a perfect way to put it.
Okay, so the engineer is the pilot, AI is the co-pilot. But looking at the report on the malicious use of AI, there's a flip side. If this AI is so powerful for building things, surely it's just as powerful for breaking them.
Unfortunately, yes. This is the dark side of digital engineering. The same algorithms that optimize a bracket for strength can optimize an attack for destruction.
And what does that look like in practice?
Well, think about how the AI designed that NASA bracket. It explored thousands of options to find the optimal shape. Hackers can use that same logic for automation of vulnerability discovery.
Meaning?
Just as the AlphaGo AI found interesting moves in the game of Go that no human had ever thought of.
Right.
An AI can scour software code to find interesting vulnerabilities that no human security analyst ever noticed.
So it finds the open window that nobody knew was there.
Then it exploits it.
Yeah.
The report outlines a hypothetical scenario they call wanna laugh,
Sound like a bad joke.
a very expensive one.
Yeah.
Imagine a ransomware that uses AI to constantly rewrite its own code. Usually, security companies find a pattern, a signature, and write a patch to stop malware.
Okay.
But if the malware learns and evolves, like a video game player, it can bypass those patches instantly.
It evolves faster than the defense. It's polymorphic.
That is the fear.
Hmm.
And it's not just software. We're talking about physical threats, too. Drones.
I've seen the videos of drone swarms. They look like a flock of birds. It's terrifying.
And it's a very hard thing to stop. In 2018, there was an assassination attempt on the president of Venezuela using drones. In 2019, there was that attack on the Saudi Aramco oil facilities.
And that was a swarm, right?
Yes, a swarm of 25 drones operating in unison. When you combine that with AI navigation, you get a weapon that is very cheap but very destructive.
Wow.
The swarm just follows simple rules: don't hit your neighbor, fly toward the target. But the group behavior is incredibly hard to defend against.
And there was something in the notes about face morphing. That sounded like it was straight out of a spy novel.
It's a serious identity threat. You take two faces, say yours and mine, and you merge them into one photo. It looks enough like me to pass a human guard, but enough like you to fool the passport control AI.
So one passport could work for two different people?
Exactly. It tricks the border security AI. The takeaway here is that as we build these digital twins and use AI to design our world, we are increasing the attack surface.
So we need AI fighting AI.
We do. We need active countermeasures.
Yeah.
We can't rely on human speed anymore.
Before we wrap up, I just want to touch on the how. We've talked about AI evolving brackets and learning vulnerabilities. But strictly speaking, how does a machine actually do that? What's the math behind the magic?
It's actually surprisingly intuitive. It's based on trial and error, which is a lot like reinforcement learning. Think of a soap bubble.
Okay, I'm picturing a bubble wand.
If you dip a wireframe into soapy water, the film naturally forms a shape, right? It doesn't know math. It doesn't have a CPU. But it naturally finds the shape with the minimum surface area. It optimizes itself to the lowest energy state.
It solves the physics problem just by existing.
Right. Now,
Yeah.
in AI, we use a strategy that's often compared to a bacterium. There's this biological concept called run and twiddle.
Run and twit it.
Yeah. If a bacterium is moving towards food, so if life is getting better, it keeps running straight. If life gets worse, if the chemical signal gets weaker, it stops and twiddles. It just moves randomly until it finds a better direction.
That's actually a really good life philosophy. If things are going well, keep going. If not, shake things up.
It is. And that is essentially what these neural networks are doing. It's a process called gradient descent. They run a simulation. If the stress on the bracket is high, that's bad, so they twiddle the design.
You try something new.
Right. If the stress goes down, that's good, so they keep going in that direction. They're just minimizing the error to evolve the perfect part.
So that NASA bracket is basically just a very smart metallic soap bubble.
In a mathematical sense, yes. It's finding the path of least resistance.
So what does this all mean for our listeners? I mean, we've gone from NASA's twin spaceships keeping astronauts safe to AI that grows parts like bones, and now we're facing the need to stay one step ahead of the wanna-lefts of the world.
I think the big conclusion is that the future isn't about AI replacing engineers. It's about engineers evolving.
Leveling up.
Exactly.
Yeah.
The value of an engineer is shifting. It's moving from the act of drawing, the manual task of creating geometry, to the act of understanding.
So the engineer of the future is that architect of constraints.
That's it. The better you can describe the problem, the loads, the heat, the materials, the better the AI can solve it.
It's not about having the answers anymore. It's about asking the right questions.
Spot on. If you can define the constraints, you control the output.
That is a lot to think about. Whether you're designing a spacecraft or just trying to organize your wiring harness, the tools are changing the game.
Absolutely.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together. Thanks for listening.